Okay, so I was explaining to you that if you don't understand something, and this something could be English or mathematics, please complain and ask questions. So what I want to do today is to discuss problems that I believe are elementary and interesting. I want to discuss curves in the plane. So I will start with very, very old theorems, and I hope to show you one open question I wish I could solve, or maybe you could solve. So that's my main motivation, to go until some point you can try to solve a question. So let me begin by some very, very old theory, few centuries old, the concept of osculating circle. Most of you maybe don't know the object as circle of curvature. So let me give you the standard definition. You have in the plane a curve, it's a blue curve, and on that curve you have a point. And the idea is that you want to approximate that curve as much as you can by a circle. So the trick is very easy. You just choose 3 points on the circle, on the curve, and as you know, between given 3 points in the plane, there's a unique circle going through these 3 points. And now what you do is that you take the 3 points and you approach them to a single point. And you look at the behavior of this circle when the 3 points move together. And it turns out that at the end, when the 3 points collapse to a single point, the circle will converge to a limiting position called the circle of curvature, or the osculating circle. It seems that in Latin the word osculate means to kiss. So the idea is that the circle is kissing the curve. Okay? Okay, so let me show you something. Look at this gray region. This is the region between the circle in red and the curve in blue. It is some kind of a circular angle. You have to know that today we mathematicians call angle the domain between two lines. But a long time ago mathematicians called angle the zone between two curves, which not necessarily are lines. So here you see some kind of circular or curvilinear zone in gray. And the point is that if you take a circle which is smaller than the osculating circle, it will be outside of the gray region from the interior, so to speak. And if the circle is too big, it will be outside. So what you have to have in mind is that in this gray region, there is no circle which goes inside it. If you go to the very old books describing circle of curvatures, when I say very old, I mean 2 centuries old or something like that, you will see this as a definition of the circle of curvature. It is the only red circle which, together with the blue line, the blue curve, determines a zone which does not contain any other piece of circle. That's definition. Okay. The next point I want to show you, something very important that many people don't know, even good geometers, is that if you continue the blue curve in the other direction, like that, it will go outside of the circle of curvature. So what you have to keep in mind, that's very important, is that if you take a curve and if you draw the circle of curvature, then the blue curve enters from outside to inside the circle of curvature. Usually, if you ask somebody to draw a curve in the plane, he will draw a curve. And if I pick a point here and I ask you, can you draw the circle of curvature? Usually people do like that. Very bad. This is not like that. The circle of curvature is like that. Yes?
However, I must point out that
Is in the generic. Yeah. What is not always true, you mean?
cannot the picture draw
Because?
cannot be true because of the reason you just mentioned. The arc of the fine circle enters the gray domain on the other side. It's too flat. On the left it's too flat.
Oh, you mean my picture is not correct?
Yes.
Yeah. Okay.
You have the arc.
Okay. Okay.
Enters.
Well, okay. You're right. You're right, Victor. I did the picture by hand, and in a few minutes you will see computer pictures, better pictures. Anyway, so you have to keep that in mind, that the circle of curvature, so to speak, crosses the curve. Okay, now we have definition. Let me give you a theorem. The theorem has a nice story. Maybe 15 years ago I was very happy because I proved it. Then I showed it to a friend, and the friend said, no, Etienne, this is not your theorem, this is my theorem. And then I looked in books and I discovered that this theorem of my friend was not due to my friend, but in books you find it under the name of Kneser, 1920 or something. And then very recently, I mean 1 year ago, I was reading old books. I like old books, and I discovered that it was known to Tate 100 years ago. So I don't know who proved it, and nobody cares. But let me give you the theorem. So this is the paper of Tate, the oldest paper I know on the subject, giving the proof of the theorem. Here's the statement. You take a piece of curve, a blue curve, and you assume that on this curve the curvature is monotonic. So it's increasing or decreasing. And now you draw two circles of curvatures at two different points. And the theorem says these two circles do not intersect. They are nested. One sits inside the other. So if you ask somebody to draw a curve and then the collection of all circles of curvatures, usually people drew something like that. This is totally wrong. This is not correct. Circles of curvature usually are nested, one inside another. So that's the theorem. Oops. This is my... Before I give you the proof, I'd like to show you what I call a disproof. I will show you that this theorem is not true. Okay? So I will give you the proof that the theorem is not true, and I hope you will find a mistake. So why the theorem cannot be true? Well, suppose it's true. So that would mean that if you take this blue arc with increasing curvature, all these circles of curvature should be 2 by 2 disjoint. So they should define a collection of circles which don't intersect each other. So if the theorem were true, we would have a collection of a nested family of circles. But now, if you have the blue curve has to be tangent to these circles. at each point. Because of course, the curve and the osculating circle are tangent. So you have this strange fact that you have a collection of smooth curves, red curves, the circles, and the blue curve is always tangent. So how can it escape from being a single curve? Think about it. You have a family of disjoint curves. This is something that we mathematicians call a foliation. And we have a blue curve which is always tangent. And at the same time, it has to go from one curve to the other. How is it possible? It looks like contradiction. Look, here's the simplest example. Suppose you take the collection of vertical lines. And suppose you try to draw a curve, a blue curve, which everywhere is tangent to the vertical. So the velocity would be always vertical. So if the velocity is always vertical, its horizontal projection is 0, so the horizontal derivative is 0, so the projection should be a constant. So the blue curve should be a vertical curve. But it cannot be, because it should be contained in a red curve. You see the contradiction? You have, if the theorem is correct, the family of osculating circles is some kind of smooth foliation like that, and the blue curve does not know how to do. It has to be tangent, and at the same time it has to go from the inner circle to the outer circle. So where is the contradiction? Well, the contradiction is that the family of circles given by the osculating circles is not regular, is not a smooth family, is not a differentiable family. Well, let me show you some example. Here I drew an helix, a spiral, in blue. You have a yellow point, and the yellow point will follow the spiral. And I will show you a little film where you will see the osculating circles moving as the yellow point is moving. Look. I like this picture. It's a family of circles. Thank you, thank you. There's more to come. So it's a family of circles, and they don't intersect 2 by 2. But if you look carefully, they almost intersect along the curve. They don't intersect, but they almost intersect along the curve. On the location of the curve, you see that the density is higher. And since the density is higher, it is a sign that the distribution of circles is not regular, is not smooth. Okay? Victor?
Yes. Again, maybe I'll add a small comment in Russian first.
Okay.
Итак, смотрите, что произошло. Если бы соприкасающиеся окружности более-менее как концентрические, замена координат могла бы их превращать в горизонтальные прямые, и условие пересечения касания означало бы, что производная уровня равна нулю. Чего не бывает, потому что функция производная даже если ноль константа. Поэтому, хотя каждая отдельная окружность замечательная, то, как они разбивают плоскость, вещь плохая. Если вы видите то, что кривая стала красной, Это потому, что при маленьком сдвиге на небольшое расстояние дельта далеко от точки, в которой проведен соприкасающийся окружность, она сдвинется как раз на это самое дельта, а вот вблизи изменится очень и очень мало. На степень дельта, там, на корень или на корень кубический. Ситуация, когда происходит такое, называется словом Гёльдерова зависимость, когда зависимость результата от аргумента это всего лишь корень, а не нечто главное. Поэтому кривая была нарисована, и от нее теперь осталось, и она вся теперь закоснилась, потому что точка шла с очень маленьким шагом. Извините, я вам собрал. Кривая была.
Странный,
твоя правда, извини, Слава. Впадается в кубе, то есть наоборот, восстанавливать дельта по точке это бывает не то. Sorry, Этьен, I spoke a bit about Hölder dependence.
Okay.
So
Oh, you explain Hölder? Good.
I said what the word Hölder means and
Okay.
what the word distribution means.
Okay, so I wanted to suggest as an exercise to compute circle of curvatures for the helix and to check if it is Hölder, and if it is Hölder, to check with each exponent it is Hölder. That's a good exercise for you. Okay?
I didn't do it.
Okay.
I even almost did not declare
Okay. Okay, so now I want to make some comments about regularity of foliations, of distributions of curves. Let me begin by a very simple observation, which is due to my colleague Zegib. Suppose you have some domain in the plane. Here it's the interior of an ellipse. And suppose that inside you have a collection of segments, like that. And assume that these segments do not intersect. And then the claim is that this implies automatically some kind of regularity for the distribution. What I claim is that this implies that the distribution is Lipschitz. So let me explain that. If you take two vertical lines, these black verticals, on the left and on the right, then you can take a point X on the vertical black line, and you can slide along the red line to go to h of x. So each time you have this kind of picture, and each time you give me two vertical lines, these two black vertical lines, you get some homeomorphism h going from the first to the second. And the claim is that if these red lines are lines, straight lines, then this h, this homeomorphism h, has to be automatically a Lipschitz map. Is the concept of Lipschitz well known? Yes? So why? That's a simple exercise. Look, if x and y are very, very close together, say 1 millimeter, and if h of x and h of y are very far apart, let's say 10 centimeters, then the two straight lines, x, h of x, y, h of y, will be forced to intersect inside the domain. This is not possible, by assumption.
But the domain may be too small.
The domain, okay, but given the domain, if the domain is given, then there is a Lipschitz constant such that. Okay? So that's a good exercise. That's a good idea. That sometimes the geometry of the curves implies some regularity for the distribution. Here's an exercise. Suppose that instead of taking lines, I take circles. So, same picture, you have some domain in the plane, and inside the domain you have pieces of circles. And you assume that these pieces of circles do not intersect. And the question is, does that imply something for the regularity of the homeomorphism H? Does that imply that H is Lipschitz, for example? What do you think? It cannot imply Lipschitz because of Tate theorem, Tate-Kneser theorem. Because the family of osculating circles is indeed a family of circles which are disjoint 2 by 2. And if it were Lipschitz, then one could use the Cauchy-Lipschitz theorem claiming uniqueness of solutions of differential equations. And that would be contradiction. So it cannot be Lipschitz. But does that imply, I don't know, Hölder, for example? Does that imply Hölder with exponent 1/2? Or does that imply something? Have a guess for that?
Sorry, what's Hölder?
Victor told me he explained what it is. No?
Not at all.
Okay. So a homeomorphism H from R to R is Hölder if H of X is bounded by some constant, some alpha. Okay? This is the Hölder continuity. When alpha is 1, it's Lipschitz. And the answer is no. This does not imply anything. And this is a theorem due to my colleague Zegib, which is not obvious at all. The theorem is this. If you give me any homeomorphism, anyone, from a piece of a line to a piece of a line, it is always possible to connect X and H of X by a piece of a circle in such a way that the circles do not intersect. Okay?
Should the memorphism preserve the order of the points?
Yes, it's orientation preserving. Yeah. So for every homeomorphism which is orientation preserving, it is always possible to connect each point with its image by a circle going a little bit beyond X and Y, covering some open sets, such that the circles don't intersect.
Well, the two lines are vertical.
The two lines are vertical and parallel. Huh? Okay,
Theorem or
that's a theorem. That's a non-trivial one. If you replace the word circle by interval, then the answer is no, it has to be Lipschitz. So you have to prove that you have enough flexibility in the space of circles to connect, to interpolate.
arbitrary function.
An arbitrary function is,
One arbitrary.
yeah, you have one arbitrary function and you want to connect it without intersection.
You take one arbitrary.
It looks like an exercise, but it's subtle one. Okay, now I think it's time to prove the theorem of Tate and Kneser. Let me give you, I hope at the end of the talk you will have two proofs. But let me give you the first historical proof. Okay, so I should explain this picture first. In blue, you have the original curve. Q is the center of curvature, the center of the osculating curve or the osculating circle at P, and Q prime is the center of curvature, the center of the osculating curve at P prime. I want to prove that these two circles, these two red circles are disjoint. Okay. And what you see in orange, or yes, orange, Q prime, is the locus of the centers of curvature of all the points between P and P prime. In English it's called the evolute. This is the evolute of the original curve. And what you probably know, is that there is a kind of a mechanical definition of the center of curvature. If you take a wire, une corde, comment on dit corde? Comment? A string. You take a string, and if you put this string at the point Q, well, and you tighten it from Q to P, it's a string, and then you fold the string along the curve Q prime. When this string will fold, the point P will follow the original curve, the blue curve. Okay, so this is the classical fact, a very well-known fact. So you take this Q prime, you take a string and you fold it like that, and the string, the end of the string will follow the curve P prime. This is the mechanical definition of the center of curvature. Now you just write the equation that the length of the string, which is QP, is equal to the length of the curve QQ prime plus the length of the string Q prime P prime. Now the length of the curve QQ prime is bigger than the length of the segment QQ prime, so you get that the distance between Q and P is bigger than QQ prime plus Q prime P prime. And this precisely means that the two circles don't intersect. End of proof. Is the proof okay? Yep. Yep.
Who needs a translation? Who does not?
Well, no need for translation, just one picture. The picture is that. Okay, so it's the original proof. Now, let me try to go for some other theorem. This one has several good aspects. One, the proof is trivial. Two, I like it. And three, I think I proved it, but I have no idea. Maybe it was known much before, since it's so elementary. Here's a very elementary theorem. It is a theorem which deals with Taylor polynomials. Well, I'm sure you all know that if you take a smooth function on some interval AB, then you can define the Taylor polynomial here that will be of even order. It's a polynomial of degree 2k, and I've written here the Taylor formula. Okay? So for each point t in the interval AB, I have a polynomial. The polynomial given by this formula. Okay. Theorem.
In x large.
What?
A polynomial in x large.
Yes, it's a polynomial in x large at the point t. Okay? So just to show you some picture, this is the exponential function, and then I show you the polynomials, Taylor polynomials of degree 2, 3, 4, 5, etc. And they approximate, as you know, better and better the curve. Theorem. Theorem is this. Suppose you have a function on some interval AB, and assume that some derivative of odd degree 2k plus 1 does not vanish on the interval AB. then I claim that if you draw the graphs of the polynomials, or I should say, this is not clear here, of degree 2k, then they don't intersect. So maybe, sorry. This is incomplete here. It should be then the graphs of the Taylor polynomials of degree 1 less 2k don't intersect or disjoint. So here's a picture first. This is exponential function, and I'm drawing the Taylor polynomials of degree 2 at every point. Taylor polynomial of degree 2 is just a parabola. And you see the picture, they don't intersect, 2 by 2. The exponential function has a third derivative, which is not 0 everywhere. So the polynomials of degree 2, which Taylor polynomials of degree 2 don't intersect. That's the picture. Of course, you see some kind of similarity between this theorem and Tate's theorem that the circles of curvatures don't intersect. There is something in common. And what I want to try to convince you today is that what is this thing in common? And I hope it will give some nice open questions. Here's the proof of the theorem. So we have a map from the interval AB to the vector space of polynomials. For each t, we have a polynomial of degree 2k. Then, well, you know the formula. The formula is this one. I propose that we take the derivative of this map. It is a map from an interval to a vector space, so I should be able to compute the derivative of the polynomial with respect to little t. So, maybe I'm not good with computation, but maybe you can help me. I'm sure you are better than me. Let's compute derivative. So I should take the polynomial, which is f of t plus f prime of t x minus t plus So can we take derivative of that? Derivative with respect to t, little t. So derivative is easy, is f prime of t. Here I get two terms. The first one is minus f prime of t, and the second one is and each time I take derivative of one of these terms, it will cancel with the previous one, and they will drop. And only one will be left at the end. So the formula is this, okay. Only one term is remaining. Okay? So since you have that, you have the value of derivative, you can compare the Taylor polynomials in 2 points, in A and B. The Taylor polynomial in B minus Taylor polynomial in A this difference is equal to the integral of derivative. So I get Taylor polynomial B minus Taylor polynomial A is equal to the integral from A to B to the derivative that I computed here. Now the assumption of the theorem is that the derivative of order 2k plus 1 does not vanish. Say for example it's positive everywhere. So if it's positive everywhere, the integral of a positive function is positive. So you get the difference is positive, and in particular the two Taylor polynomials do not intersect because the difference is positive. End of proof. So this is a very simple observation. I would be curious to know if somebody made it before. It's so simple. Okay. Okay. So you see there is something in common between this little theorem concerning Taylor polynomials and Tate theorem concerning circles of osculating circles. Let's try to understand what is in common. The thing which is in common is differential equations. I will discuss differential equations, very general differential equations of odd order. So it's a functional f of x, y, y prime, etc. y derivative 2k plus 1. So as you know, if you take a differential equation, if you take some initial condition, locally there is only one solution starting from this point. If you have a second order differential equation, you have to give the initial point, initial velocity, and then you have a unique solution. If you go to a differential equation of order 2k plus 1, you have to give 2k plus 1 initial conditions, and then you have a solution, locally at least. The same thing is true.
Is it true for a general differential equation, or is it true for only a differential equation where of the form y to the 2k plus 1?
It must be expressed.
Yeah. That's you are completely right. If it's not explicit, I may be wrong. But let me give something for the full talk. My talk is generic, meaning that I don't. For example, a few moments ago I said the curve will enter the circle of curvature.
Yes.
This is true, but it is not always true. Okay, it's generically true. Okay, so what I want to discuss today is generic properties. So I take a generic differential equation, and you are completely right. Okay. Anyway, so now we can play the following game. We have a curve. Okay, so we have our differential equation. And then you have our curve. And you pick a point on that curve. And we look for solutions of the differential equation which approximate as much as possible the curve. Since we have a differential equation of order 2k plus 1, we have 2k plus 1 free parameters. At the beginning I told you, given 3 points in the plane, there is a unique circle going through these 3 points. In the same way, if you give me 2k plus 1 points on the curve, usually there is a unique solution of the differential equation going through these points. Usually. Okay? So what you would like to do is to take this unique solution of the differential equation going through these 2k plus 1 points and coalesce them to a single point. 1 second, Victor. And then you hope that this solution will converge to a limiting position, And this limiting position, you will call it the oscillating solution to the curve. Victor?
Sorry, maybe, however, I would like to wait 1 more minute for a Russian summary. Итак, что происходит? Вместо того, чтобы говорить о прямых или об окружности, мы говорим о дифференциальных уравнениях. Дифференциальное уравнение какого-то порядка. То есть нас интересуют функции y от x, которые дают какому-то соотношению на производные. Например, прямые задаются очень простым соотношением на производные. Вторая производная равна нулю. А можно работать с экспонентами. Первая производная равна значению. А можно с экспонентами с еще неизвестным показателем. Это будет опять уравнение второго порядка. И так далее. Хорошее упражнение научиться задавать окружность дифференциальным уравнением. Тоже не шибко сложно. Так вот, если у вас дифференциальное уравнение порядка 2k плюс 1, то первые 2k производных задаются как угодно, 2k плюс 1 уже вылезает из уравнения. Соответственно, получается 2k свободных параметров от нулевого до от нулевой, то есть значения, до 2k производных. 2k плюс 1 свободный параметр. Соответственно, можно зафиксировать эти параметры так, чтобы в данной точке касание решения с уже нарисованной кривой было бы максимальным. Просто сначала берем значение, потом производную, потом вторую производную, для в точности как нарисованной кривой. А дальше решаем декор. 2k плюс 1 параметр нашли совпадение с 2k плюс 1, а все остальное уже от нас не зависит. Называем это дело соприкасающимся решением. Точно так же, если мы работаем с прямыми, это касательное, а если с окружностями, соприкасающиеся. Этьен, je te rends le mot avec 3 minutes de plus.
Okay, so I hope Victor explained what is the concept of oscillating solution. Okay? Okay, now here's a picture. We have this blue curve, and the red curve is the oscillating solution going through 3 infinitesimally close points on the curve. Just like we had in the case of oscillating circle, it's just a more general concept. For each general differential equation, we have this concept. Now, if we take 2 infinitesimally close oscillating solutions, each one of them intersect in 2k plus 1 points, consecutive points, so 2 of them intersect on 2k points. Here's a picture. You have one oscillating solution in green, intersecting on 3 points, and so to speak, the next one intersects on 3 points, just slightly further on the curve. So the 2 intersect on 2k points, which mean that locally they don't intersect, because 2k is an even number. And you have this local picture. So here's my claim, that if you take a generic curve, a blue curve, and if along that curve you take all solutions, oscillating solutions to that curve, they will behave like the green, the red, and the gray curve. They will not intersect locally. So this is the general principle. The general principle is that oscillating oscillating solutions of differential equations of odd order do not intersect locally, just because 2k is an even number and 2k plus 1 is an odd number, not more than that. Let's look at some examples. I will write some differential equations and you have to guess what are the solutions. Polynomials. So in the case of polynomials, the corresponding statement is the statement on Taylor polynomials not intersecting. What is this differential equation?
Maybe a circle.
Circles. The general solution of this differential equation consists of circles. It's a third order differential equation whose solutions are circles. What about this one?
Fractional linear.
Yes. This is called the Schwarzian derivative, and the general solution is given by the Möbius transformations or the fractional linears or whatever, the homographies, ax plus b divided by cx plus d. And then you get a theorem for them. You take a curve in the plane, and for each point you look at the osculating fractional linear. They don't intersect. This is a differential equation of order 5. It's big determinant. Can you guess what is the general solution of this differential equation? Well, you can guess it because we all like geometry. Conics. A conic in the plane is a curve depending on 5 parameters. Okay? The space of conics has dimension 5. So it's a good idea to look for the general differential equation whose general solution is conics. And this is what Monge did. And this is the solution. Well, this is a way of writing it. It's a determinant involving 5 derivatives. And I promise this is true. The general solution is given by conic. Okay, so we should expect a theorem concerning conics, osculating conics. Okay, here's a theorem which is exact analogous to Tate theorem. If a curve does not contain sextactic points, so if the curve is generic, then the osculating conics are disjoint, just like the osculating circles. The osculating conics are disjoint. How do we prove that? Well, if you take 2 consecutive osculating conics, locally they intersect in a point of order 4. But for 2 conics intersect in at most 4 points, so they don't intersect at all. Here's the picture you should have in mind. Just the way we had osculating circles nested, you have osculating conics which are nested. Here's the little film, the same film as before, except that now I'm not drawing the osculating circle, but I'm drawing the osculating ellipse. The contact is better with ellipses than with circles. And you have the same picture. The ellipses do not intersect. Basically with the same theorem, same proof. Here's a question that seems natural. Once we prove a theorem, we want to know if the theorem is the best. So here's a very natural question. You take 2 circles, one sits inside the other, and 2 points on the circle, these black points. Now you ask yourself, is there a curve with increasing curvature going from the first to the second? Is it possible to get some kind of converse to Tate's theorem? If 2 circles are disjoint, they behave as circles of curvatures of some curves with increasing curvature. That's an exercise, and the answer is yes. Yes?
Sorry, I'm afraid not everybody is familiar with this geometrical term.
Which one?
Vertex.
Oh. Explain that.
Кривая, то ее кривизна обычно, когда вы идете, меняется либо в одну сторону, либо в другую, либо подрастает, либо убывает. Точки, где происходит смена направления, называются вершинами. Sorry, I gave the definition.
I don't know what the definition you got, but I would say this. If you take a point on a curve, take the circle of curvature, usually this quantity here is small of order 3. It's an epsilon cube. Sometimes it is much smaller than that. It could be epsilon 4, epsilon 5, etc. For this kind of point, one says it's a vertex. Now, what's happening for conics? I told you conics are nested. Is there a similar theorem? If you have two conics, one sitting inside the other, is it possible to connect the two by a curve in such a way that between these two curves we have no sextactic point? Sextactic point is the analogous to vertex for conics. Is it possible? In other words, the theorem I mentioned, that if you go along a curve, the osculating conics are nested, is it possible to improve it? And there the good news is yes. Or no. I mean, no, it's not possible. The answer is no, okay. Which means yes, it's possible to improve it. Here's the theorem. Victor, 74 minutes leads to a quarter to 11. Huh? Victor?
Yes, I'm just checking. You have 6 minutes in a standard way plus 3 plus. Well, I say at least 11 more minutes.
11 more minutes.
No, you have 20 minutes. You have 20 minutes. Also, using my position as the scientific director, I will probably add a few minutes.
Okay. Okay. Thank you.
You definitely have a minimum of 30.
Okay. So. Let me mention the theorem that I like, and I wish I could understand it better.
Much more time.
Yes, Etьен, your lecture started not at 9:50, it started at 9:30.
Aha.
So,
Aha. Okay. Okay. So here's the question. Consider the set of conics. This set of conics is a 5-dimensional object. Now, in this set of conics, there is a very natural order relation. That one say that one conic C1 is contained in another conic C2. Is that clear to you? Is it clear to you that a conic in the plane has an interior and an exterior?
Non-singular.
Let's say non-singular conic. Okay? So I say that C1 is smaller than C2 if the interior of C1 is contained in the interior of C2. It's a very nice ordering in the space of conics. And this ordering is invariant under projective transformations. Now my discovery, and I was very happy with this little discovery, is that there are more orderings in the set of conics than just this simple-minded ordering. There is a more subtle way to define an ordering. So let me give the formal statement. Theorem. There is a family of partial orderings denoted by contained sub lambda on the space of non-singular conics in the real projective plane, depending on the parameter lambda from 0 to 1, with the following properties. 1, it is invariant under projective transformations. 2, when lambda is 0, it is nothing more than this simple-minded relation. 3, when lambda increases, the relation becomes stronger and stronger. So when lambda is less than mu, and if a conic C is contained sub mu in C prime, then the conic C is contained sub lambda in C prime. 4, I should define what this means, but there is no other way to do it than these two. I mean, there is only one family of ordering. And then one can improve Tate's theorem, that if you take a curve, and if you look at the osculating conics along that curve, not only the curves are nested for the silly, obvious ordering, but moreover, they are nested for the strongest sub-1 inclusion. Is the statement clear? And finally, the converse is true. If you have two conics, one being included sub-1 in the second one, then it is possible to connect them by a curve, blah, blah, blah. Now, what I should explain you, what is this inclusion sub lambda? And the answer is, I'm sorry, I don't know. I mean, I'm going to give you a formula. I will give you a definition. But from the geometric point of view, it's total mystery for me. So I'm going to give you a definition of an order relation in the space of non-singular conics in the plane. You will see definition is not complicated. But the meaning for me is mystery. So here's the definition. Yes, Victor?
May, as it's complicated, may I read in Russian to verify that everybody knows. Итак, что происходило? Мы видели, что сначала соприкасающаяся окружность, а затем соприкасающиеся решения дифференциала оказывались вложенными, просто геометрически не пересекались и жили один внутри другого. Теперь Этьен говорит следующую вещь. Давайте посмотрим на пространство всех коников, на пространство всех кривых второго порядка. Эллипсов, гипербол, парабол, наклонностей. Не особых, то есть пару пересекающих прямых запретив. Можно определять на таком деле частичный порядок. Простейший способ это сделать, это говорить, что одна кривая меньше другой, если она лежит внутри. Это частичный порядок, потому что если две кривые пересекаются, то ни одна из них не меньше другой. Он очевидно инвариантен относительно проективных преобразований. Внутри это вполне корректно определенное слово. Оказывается, что таких порядков много. Их однопараметрическое семейство. А именно, они все больше и больше становятся все более и более сильными. То есть, если было вложение с большим параметром, то есть и с меньшим. Так вот, то есть можно сравнивать все меньше и меньше, и наоборот утверждение о сравнимости все более и более сильно. Так вот, оказывается, что пока нет точек конического уплощения, пока нет точек, где коника касается сильнее, чем имела бы право в проходящего положения, есть сравнимость последовательная соприкасающихся коник, соприкасающихся второго порядка. Не просто по вложению, как мы уже обсудили, а в сильнейшем возможном смысле. И именно это сейчас и будет обсуждаться. А именно Этьен сказал, что он задаст эти сравнимости формулами, про которые он не готов сказать, что такое у них геометрические сюжеты. И что ему интересно, как это делается. Étienne, je te rends la parole, je t'ai pris encore 3 minutes. Лекция про историю.
Okay, so let me give you the definition of the strongest relation, inclusion 1. Again, the definition mathematically will be complete, but from the psychological point of view, it's total mystery for me. Here's the definition. Suppose you have two conics, C and C prime. Of course, you know you can define them by equations. The equation is given by a symmetric matrix, 3 by 3 matrix. If the conic is not empty, it means that the symmetric matrix should have two positive eigenvalues and one negative. Okay? So the point is that a given conic has many equations. If you have one symmetric matrix, you can multiply it by a constant. It's another symmetric matrix given the same, defining the same conic. So what you can do is they can normalize in such a way that they have the same determinant. So you have your two conics C, C prime, and you choose equations for them having the same determinant. That normalizes the choice of the constants. And then you define C to be contained sub 1 in the other if the difference A prime minus A is definite positive. That's definition, totally computable, of an order relation. Let me check some examples. Consider the circle x squared plus y squared is equal to 1, and the ellipse x squared divided by a squared plus y squared divided by b squared is equal to 1. What does that mean to be contained 0 in the usual sense? Well, that means that a and b are bigger than 1. To say that the ellipse is contained in the unit circle. What does that mean to be contained sub 1? Well, you do the computation. You take the 3 by 3 matrix, you normalize, blah, 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 and here's the result. The second conic should be, so to speak, round. Should have x's a and b such that b is less than a squared and b is more than root a. So one conic is inside the other one, but it's sitting in a round way, so to speak. So I would be very happy if somebody could find a very nice projectively invariant definition of what does that mean to have such round convexity or something like that. I have no idea. Anyway, you see that here you have a better theorem that if you go along a curve, not only the conics are disjoint, but they are strongly disjoint. Okay, how about going to a higher degree? Here's a differential equation. Aha! So in order to simplify notation, I denote it by a sub I, the ith derivative divided by I factorial. And this is the determinant involving derivatives up to order 9. Cubics, of course. Yeah? Cubics. if you look to algebraic curves of degree 3, cubics, they depend on 9 parameters. So Alphen, towards the end of the 19th century, wanted to understand the general differential equation having as a solution the general cubic, and then he wanted to understand how a cubic can osculate a curve. You give me a curve, give a point, and you look for the best cubic that approximates it. So using my terminology of today, it will be a cubic that will have in common with the curve 9 infinitesimally close points.
9.
Okay? Okay, so we hit against a famous paradox in algebraic geometry called the Kramer paradox. So I should explain that quickly. If you count how many parameters there are in algebraic curves of degree d, you count coefficients, you see that the number of parameters is d plus 3 plus divided by 2. For example, if d is equal to 2, conics, you find 5. Conics depend on 5 parameters. When d is equal to 3, you get 9. Cubics depend on 9 parameters. When d is equal to 6, you get 27 parameters. Okay. Now, you have this Bezout theorem that says that in general, when you take two curves of degree d, they intersect in d square parameters, in d square points. Two conics intersect in 4 points. Two cubics intersect in 9 points. Two sextics intersect in 36 points. And you'll see this strange phenomenon that as soon as d is big, 3 or more, d square becomes bigger than d plus 1, d blah blah blah. In other words, the number of parameters for describing the curve becomes smaller than the number of intersection points of two members of this family. This is a terrible situation. It took more than 100 years before mathematicians could understand that. If you take two sextics, for example, they intersect in 36 points. But these 36 points are much, much more numerous than the poor 27 parameters necessary to define sextics. In other words, the intersection of two sextic curves is a set with 36 elements, very non-generic. These 36 elements have to be very specific. So that's something which is not easy to understand, and if you don't understand it, don't worry. I don't either. It's rather difficult to understand. Yes?
If I'm not mistaken, we know a simple appearance of this situation under the name of Pascal's theory.
Yes.
Yes.
Yeah. But that would be. Yeah, I would love to explain that, but that would take me the time which is left.
Okay.
Or maybe okay. I think anyway. Okay, so the conclusion is that as soon as d is 3 or more, it is still true that osculating algebraic curves of degree d do not intersect locally. But this local property is not enough to guarantee no intersection globally. Let me show you a picture. In the case d is equal to 6. In d is equal to 6, the number of the space of sextics depend on 26 parameters. and intersection of 2 sec 6 is 36 points. So here's the picture you could have in mind. The red curve, I'm sorry, the blue, take the blue curve. The blue curve is our old friend, the original blue curve. There's a black point. On this black point, I drew a sec-stick curve osculating. Okay? Having how many points in common?
26.
Having in common with the curve 26. Yes, having 26 points in common, because I have 26 free parameters. Okay? But two curves, 26, 10 points are missing, because 36 is 26 plus 10. So there could be 10 additional yellow points. But this is a picture I don't know, and this is the final question I will ask you. Have no idea if this kind of situation do occur or not. This is not an actual picture, it's just a drawing. Have no idea if it's possible to do it in practice. I will make the question precise in a second. But this is, you see, locally, everything is okay, but globally we might have problems. There is still one case in which I can say something. The case of cubics. Why? For oval, you know, a cubic might look like this yellow curve. Has a branch, infinite branch, and some kind of closed loop that people in algebraic geometry call that oval. It's the oval of a cubic curve. And the point is that it still works for cubics, for ovals. Here's the point is this. Let me show you a picture. Again, I take the helix, and then I take the osculating cubic. Oops. You see, the ovals don't intersect, but the cubics do intersect, because the cubics contain one, you know, the cubics look like that. So when the thing is rotating, these lines do intersect. It's a total mess. Okay? The cubics do intersect. There's no way to avoid that. But the ovals don't intersect, as you can see on the picture.
Can you show the animation once more,
yeah.
please?
So you see, this is the rotating cubic, and then I will draw only, okay. Is that clear?
Only one component works.
Only one of the two components work.
Yes, works.
And this is because this is the last time Kramer paradox is not in action. Okay? After that, no idea. Okay. Now, can I take 5 minutes to open? So okay, so okay.
8 minutes.
Okay, so I take these 8 minutes to make a conjecture or ask a question. Okay? The question concerns what we discussed today, but in a higher degree. So let's choose some integer d, some degree, such that d is even and a d plus 3 over 2 is odd. So why? D even is good because I want algebraic curves with an interior and an exterior. For example, if you take an algebraic curve of even degree, you take one of its equations and you look at the place where the polynomial is positive and you call that the interior. And this is well defined only if the degree is even. So even degree curves have an interior. Now why do I want d plus 3 over 2 odd? Because I want the space of parameters to be odd dimensional. So we have seen examples. We have seen the examples of conics when d is equal to 5, is equal to 2. And the example you should have in mind is d is equal to 6. Example, d is equal to 6. So I want to discuss osculating statistics. Okay. Now you consider the space of all statistics. So you consider the space x sub d of non-singular real algebraic curves of degree d with a base point. This is space. Now I claim that on that space there is a local ordering. So let me explain that. Each time I take a curve, a generic curve, for each point I can take the osculating curve of degree d there. So each curve here defines canonically a curve in the space of algebraic curves. So each point here, each curve here defines tangent vectors in the space of algebraic curves. And I can define let me read what I said. Every smooth curve defines a curve in xd that we can orient in such a way that the interiors of the osculating curves are locally increasing. These tangent vectors generate a convex cone field in xd. So here's a kind of a picture. This is an artistic picture of xd. xd is the space of all algebraic curves of degree d. And all these little cones are the positive vectors for all curves like that. For each curve, I get tangent vector. So they generate a cone in the space of tangent vectors. And the question is, does this cone field define a global ordering? So, what does that mean? I would like to say a curve A is less than a curve B if it's possible to go from A to B following a positive curve. That would be definition. You want to go from A to B by a positive curve. But the problem is, maybe there is a loop. And that's the open question. Is there a loop, a positive loop, in the space of algebraic curves of degree d? So, in practice, the question is this. Does there exist? So, okay, let me finish by mentioning this question. Question? Does there exist some curve in the plane such that if you look along that curve at all osculating curves of degree 6, they locally are increasing everywhere. Picture. This is an osculating curve of degree 6. This is another one. This is another one. And this local picture. When you move along the curve, the osculating curves of degree 6 locally, you see on the right, locally they look like osculating circles for a curve, so they are locally nested. But when you go around, you come back to the initial point. So locally they look like being increasing, but it's a global loop. Of course, this is not contradiction, because as you can see on the picture, they have many intersection points away from the crucial points. Okay? So this is this is the question. I hope I defined for you a reasonable local ordering on the space of algebraic curves, of degree 6 for example. And the open question is it a global ordering? If the answer would be yes, that would be great, because we would have a good definition of this curve is less than this curve.
But can you say again what is the local order?
Okay. A local ordering is, you take a point in xd. A point in xd is a curve and a point. And then starting from that point in that curve, you look at all curves and all oscillating curves in all directions. This produces a positive cone. Okay, so something is locally. Let me put it this way. I want this curve to be such that when I move along it, and if I look at all oscillating curves of degree 6, at any point what I see is no intersection locally.
So it's equivalent to drawing a curve with no special points.
That's equivalent to, yeah, that's another way of saying it.
No tangents.
Yeah, it's a closed loop with no special point on it. Is there such a point? If the answer is yes,
then there is no order.
yeah. And the answer is no, then there is an ordering, and that would be nice. Okay? So I tried, I mean, this is something that the computer can check, but I don't know. I mean, I tried and I couldn't, I don't know. Yes?
Sorry, I would for permission to translate for the last time and to return the
Maybe I can just conclude.
sorry.
Okay, I concluded. On my computer file, I have more to say, but I had to be okay.
Another 8 minutes.
And what?
Another 8 minutes.
Another what?
8 minutes.
No, because I would go somewhere else. No. So what I wanted to say is that conics is a typical example of a homogeneous space. The projective group acts on the space of conics transitively, and one can think of the set of conics as G mod H. G is a big group and H is a smaller stabilizer. Anyway, what I want to say is that what I said today should be generalizable to a much more general situation for all Lie groups and all subgroups. And not only that, but I wish to do something in the infinite dimensional case. And the typical example I have in mind is the group of contactomorphisms. I mean, I just want, if you don't understand, no way. I just want to say, I mean, there are more to be done in this direction, and I try to remain as elementary as possible today, but this is just the starting point of more. Okay, so thank you.